In this chapter, we're going to do a reversal. We're actually going to start doing the reverse of differentiation, the act of finding derivatives, and start doing what's called integration, the act of evaluating integrals. Integrals and antiderivatives are very closely related. So let's first talk about what an antiderivative is. So the definition of an antiderivative goes like this. Capital F is an antiderivative of the function small f if for every value in the domain of small f it follows that the derivative of capital F equals small f. Now we can do some examples by just thinking backwards. Let's say that capital F is the function x squared. Okay, I'm sorry. That's not what I meant to say. Let's say that f prime, capital F prime, is the function 2x. Okay? So in other words, the derivative of some function is 2x. So how can I find the antiderivative of this function? So we're looking for the antiderivative of this function. So we're looking for a function whose derivative is 2x. Okay, well, I started you out on an easy one. You should easily be able to tell that if you take the derivative of x squared, you're going to get 2x. But here's the kicker. If you take the derivative of x squared plus 5, you're going to get 2x. If you take the derivative of x squared minus 7, you're going to get 2x. Well, technically, if you take the derivative of x squared plus any constant, plus or negative, then you're going to get 2x. So the antiderivative for this function 2x is actually the function x squared plus any constant, because if you take the derivative of this function, you will get 2x. So when I'm giving you this derivative here, that's actually also, you can think of this as the little f from this definition, small f. Okay, so let's take a look at this one. Let's say that small f, or the derivative of big F, is x cubed. So to find f, let's figure out what function do we need to take the derivative of to get x cubed. Well, at first we might think x to the fourth, because the derivative of x to the fourth is 4x cubed. But how can we get rid of that 4? How can we make that 4 get out of the way so I just get x cubed? Well, we can let the function be x to the fourth over 4. And then when I take the derivative of that, if you take the derivative of that, let me just show you, you will get 4x cubed over 4. And then the 4's will cancel, and you'll just get x cubed. So it turns out that x to the 4 over 4 is an antiderivative of x cubed, but so is x to the 4th over 4 plus any constant, or x to the 4th over 4 minus any constant. Therefore, if we want to find the antiderivative of x cubed, it's got to be x to the 4th over 4, which is the function, but plus any constant. Okay? Now, you must always add a constant when you antidifferentiate or evaluate an indefinite integral, and we'll do that in just a little bit. You're not able to find the constant unless you know additional information, and we'll see problems later where you can actually determine what the constant is. So, right now, let's just try to find antiderivatives by observation. So, we know if you want to find the antiderivative of x squared, it's got to be something with an x cubed with it, because if you take the derivative of x cubed, you'll get an x squared term. So, like I did before, in order to make sure that when I take the derivative of x cubed, make sure that the 3's cancel, I have to divide it by 3. So if I use x cubed over 3 as an antiderivative, then I can find that the set of antiderivatives for x squared is the set x cubed over 3 plus a constant. This one's not nearly as difficult. You know that 5 is the derivative of 5x. So since 5 is the derivative of 5x, we can let our antiderivative be 5x plus any constant. Now you also know that the derivative of cosine x, that cosine x is the derivative of sine x. So since cosine x is the derivative of sine x, then f of x would equal sine x, and look what I did. I left off my constant. That's a no-no. Okay, so it would be sine x plus a constant, and I think I did the same thing on the next one. For secant squared x, remember secant squared x is the derivative of tangent x, so the antiderivative of secant squared x would be tangent x, and again, plus a constant. Okay, we'll do a couple more. This one's not too bad. 4x, well, if you think hard enough, long and hard enough, you know that the derivative of x squared is 2x. So maybe if I use 2x squared, when I take the derivative of 2x squared, I'll get 4x. So an antiderivative of 4x would be 2x squared plus any constant. Now, they get a little more difficult at this stage, but now I'm kind of putting the x cubed and the 2x that we did earlier together. And so when you know that x cubed is the derivative of x to the 4th over 4, and you know that 2x is the derivative of x squared, so x to the 4th over 4 plus x squared plus a constant would be the antiderivative of the function x cubed plus 2x. Now you're going to see some differentiation rules later, but I'm going to go ahead and just give you a sneak preview. You're going to find that 1 over x is the derivative of natural log of x. So the antiderivative of 1 over x would be natural log of x plus a constant. Now if x is positive, you don't really need the absolute value, but the absolute value is there just to make sure that we're not taking the log of a negative number. So don't worry about that for now. And you're also going to find that e to the x has kind of a strange quality. E to the x is its own derivative. So since the derivative of e to the x is e to the x, an antiderivative of e to the x would just be e to the x plus a constant. So hopefully that gave you a bit of an understanding about antiderivatives. Now in mathematics, we actually needed some operator that would actually perform the act or tell us to perform the act of antidifferentiating or finding the antiderivative. Well, this symbol here is the integral sign or integral symbol, and it's used to represent the antiderivative of a function. By using this symbol, we don't have to say the antiderivative of f of x is such and such, because once we see this symbol, x squared. Now the dx is there to make sure you know which variable you're differentiating with respect to. Because technically you could integrate, even though it's a function of x, you could integrate with respect to another variable, but that comes in a later calculus course. Alright, so if we wanted to integrate x squared dx, we know that it's x cubed plus over 3 plus c. So the function x squared is actually called the integrand, dx is called the differential, and of course the constant c is the constant of integration. So when you integrate a function like little f of x, you generally are going to get another function called capital F of x, where capital F of x is basically an antiderivative of little f of x. So what we generally do is capital F of x is just that derivative where the constant is 0. So, in other words, if I want to integrate 2x, well, I know the integral of 2x where the constant is 0 would just be x squared. So I can just say x squared and then add any constant. I know the integral of e to the x from what I told you a minute ago is e to the x. So if I integrate e to the x, I'm going to get e to the x plus a constant. See, I'm just doing the act of finding antiderivatives using this symbol. So the integral of x cubed dx is just x to the 4th over 4 plus a constant. Now, this integral is called an indefinite integral. And you can tell indefinite integrals because there's no little numbers at the top and bottom. Here, this is called a definite integral, and we won't talk about those just yet. But I will tell you this. An indefinite integral, the result is going to be a function, whereas when you evaluate a definite integral, the result will be a number. So let's evaluate some indefinite integrals and then check. Okay, we know that negative 4 is the derivative of negative 4x. So this indefinite integral would be negative 4x plus c. And I'm going to leave it to the reader here to check, take the derivative of the result, and you should get what we had over here in the integrand, negative 4. Now, if you evaluate the integral v squared dv, now notice I'm integrating a function of v, but I'm using dv, so that's fine. All right, then I'm going to get v cubed over 3, so it's just like when I did integral of x squared, and then plus a constant. And then I'll let you differentiate this. That should be a v right there, since it's the variable's v, not x. But I'll let you check the differentiation and see that you get v squared. Now, if I integrate this, well, remember dt. Now, remember, we know that the integral of 2x was x squared. So the integral of 2t would be t squared. And since secant x tangent x is actually the derivative of secant x, then secant t tangent t would be the derivative of secant t. So its antiderivative would be secant t, and of course the sign was minus. So I get t squared minus secant t plus a constant, and you can check that. Now this one is a little more complicated, so I'm going to just give you the answer on this one and then check it. So I'm going to claim that if I want to integrate square root of x dx, which is x to the 1/2 dx, I'm claiming that the antiderivative of this is 2x to the 3/2 over 3 plus a constant. Now, if you don't believe me, let's take the derivative of the result and see if I don't get square root of x. Well, the derivative of this would be 2/3 times the derivative of this using the power rule, so it would be 2/3 times 3/2 x to the 1/2, and then the derivative of c is 0, and this shouldn't be there because c is 0, right? And then so you're going to get x to the 1/2, which is the square root of x. Now in the next video, we're actually going to see a set of rules for integration that will help us integrate some of these without having to do what I've been doing. What I've been doing is just trying to basically think in reverse order of differentiation. So if you want to see some rules for integration, then go on to the next video and you'll see the rules for integration.